every switch, electromechanical switch, most every switch, either rests in an open position or a closed position. Closed is conducting. Open, not conducting. Unless you supply sufficient voltage. Like an open switch at 4,000 volts will conduct. Okay? A certain leakage current. You can always tell when someone's never really automated anything before by how they approach a switch. They're like, okay, I'm ready to read the switch. And they like start trying to hook it up. Maybe they'll hook it up to a DIO input or an analog input. Sometimes they'll hook it up to a scope input. Sometimes they'll hook it up to an output. No clicky. I don't understand why I can't read it. So you can only measure voltage, current, resistance. Now if you were to put a switch on a DMM, you could just directly measure it. You could measure OL or some value above 100,000 that you would measure short, or some value below 1 ohm, about in that range. That would be a ridiculous use of a DMM input though. And fundamentally the way it works is it provides a known stimulus. That might be a constant current where it measures the voltage developed. That might be a constant voltage where it measures the current developed. There's only really two ways to do it. The most common way to do it is with what's called a pull-up resistor. You tie that to any potential. It'd be wise to tie it to a logic potential. 5 volts, 3.3 volts, something like that. If you go tying it to 12 volts, now you've got to measure 12 volts. If you tie it to 24 volts, now you got to measure 24. If you tie it to 300 volts, now you got to measure 300 volts. So in most cases, it's safe to assume that the pull-up stimulus on a switch is logic level. Golf carts break this. For whatever God forbidden and awful reason, golf carts send the full fucking potential to their frickin' switches, dude. It's so awful. Like the throttle switch, the direction switch. I'm fairly certain they did this to overcome noise and to value engineer. Dates back to when they were building golf carts before circuit boards. I've got a whole history of golf carts. The oldest golf carts had a motor, and just a DC motor, and in line with that they had a resistor, and you kind of had 2 throttle states, maybe 3. One throttle state is wide open throttle. So that's the battery just directly connected to the motor. You can imagine all the ways that can go wrong. Another throttle state was tip-in, where you have a pretty large, relatively large resistance in line with the motor, developing some 20-30% of the available torque. Sometimes there's a middle of the road switch, 50-60%. It's not a linear throttle. It's super inefficient. It draws the same amount of power, measured draw, at quarter throttle as it draws at full throttle. It's quite obnoxious. No circuits though. No need for them. Just relays and resistors. Beautiful simplicity. When you overvolt those, they burn up. We prefer solid state switching, PWM, right? Anyhow, it's not the topic. The topic is how to read a switch. If you put a 3.3 volt stimulus on a golf cart switch, you might find that the ground is bouncing 2 volts or 3 volts or 4 volts. Grounding's notoriously bad. That's why they came off the chassis. Chassis can be relied on. It's fucking tubular aluminum extrusions and plastic with some steel, with some tubular steel. It's not to be considered a reliable reference point. These things evolved year after year, decade after decade, for practical purposes. Now, in a more controlled environment, it is fine to use logic for a switch, especially if you're in control of the noise. So you could just attach that logic directly to the switch. And when you close the switch, it would short out that logic. And when you open the switch, it wouldn't, eh? I've seen people do that. Then you're depending on the overcurrent protection of the driver circuit. And you basically will go into, a 20 milliamp short. Maybe it thermally overloads the chip. Maybe it blows out the channel. Not a rad plan. You typically run an inline resistance. It's called a current limiting resistor. This allows you to have the voltage stimulus without developing power or dumping current. You might think you'll use a giga-ohm resistor. It's not a good plan. Too susceptible to noise. You might use a 10 ohm resistor. Not a good plan. You divide your voltage by your resistance to get your current. Well, 5 volts divided by 1 would be 5 amps, and 5 volts divided by 10 would be half an amp. Half an amp's a lot. You don't want to draw half an amp. 100 ohm resistor, 50 milliamps. Alright, if you had to. What you really want is a kilo ohm or more. 1,000 ohms would be 5 milliamps. If you can't afford that, you're in trouble. You can go up and go 10K. It's a very, very common value. It's also very susceptible to noise. I see 10K used all over the industry, and I know from many decades of engineering that it's always a noise source. Yes, it is lower current by an order of magnitude. Right? It's a little hard to read 500 microamps through the noise. Micro. Milli, micro, nano, pico, femto. Going the other way. Kilo, mega, giga. You don't need anything bigger than giga. Not in electrical. Unless you're talking, you do like 1,000 gigahertz. You can get into tera, I guess, but it's not practical. So you might run a 1,000 ohm or 10,000 ohm pull-up resistor. And this is why you keep a little bundle of those. Axial, leaded. That's if you're going to do it direct. These days, many digital outputs will have a pull-up resistor option. If you go into their firmware settings, you'll find that, sometimes they're just pulled up, right? Because people are stupid. In the old days, you would get open collector outputs. So these days, you never know. You can measure it. Most DIOs are called a digital input-output because they can be either an input or an output. You can toggle between that. Not at the same time. And they'll have an optional pull-up resistor. It's usually 20K, something like that. It's pretty soft pull-up. The softer your pull-up, the more sensitive you are to contact resistance, line resistance, line noise. Usually doesn't matter. You can add some capacitance in there if you want to wear your switch out quicker. So you have two switches. One for presence. Haven't figured out how that one works yet. Will. Just put a meter to it. Move it until it changes. And another switch for lid. At time 0, we're not even going to look at those. We're going to turn everything off. Even if it's already off, don't bother with the Corey. Just shut it off. Reset in it. Next thing, we'll look at the lid. It's either open or it's closed. If it's open, move forward. If it's closed, read the presence switch. If something is present, there's something in there. That would be out of process. It would indicate that you should open and remove. You can choose to wait for that toggle to occur or trust. When you're running back to back to back to back to back, you get tired of the toggle, but you shouldn't be running back to back to back to back to back. So that's a player's choice. I'm not a firm believer in running things more than once. If you're running it more than once, you're out of process. There's a fucking problem. So go ahead and demand the cycle. So you'll wait until presence goes clear and lid goes clear, or just the lid. Show them a picture. Place it in like that. Jiggle it a little. Bring the lid down. Press firmly on both sides. You'll hear a click, click. Check the presence sensor. Did they just close the lid? Or is there something in there? At this point it might be smashed and broken. Happens. Costly mistake. Set the current limit. Set the voltage limit. Set the output on. Delay. Measure the current. Determine. Is this first burn or second burn? That's an important one to write down, often missed. There's a big difference. If it's first run, it'll always be the same. Plus or minus 3 milliamps. Depends on the scope or the meter resolution. You don't go necking down under mid-air. If it's not the first time, it can be drawing an arbitrary current anywhere from 10 times what you expect, 5 times what you expect, compliance down real low. This is for the case where incoming units have capacitors mounted in reverse, shorts in the traces, foobar in a million ways. If they are drawing in excess of the acceptable current, which is different for something new than it is for something rerunning, treat those as different cases. I think it's tough because if it's a rerun, you don't know what firmware it's running. And that changes through time. It could be that the firmware sits there sleeping until it gets a ping of its bus. And it could be that it goes right to work, spinning in a very fast circle, drawing a lot of power. It all depends on who the firmware engineer is and what they've done. So sometimes you ignore all of that. And you just override it. You have to set some kind of sane upper limit and say, hey, look, dude, this should never ever draw this much at first start. It's just a waste. Why would it? You're going to feed that back up the chain. Let them know that at first turn on, they're drawing a bunch of power. It's not uncommon. In the old days, a firmware engineer was really close to the hardware. And so they were very in tune with their voltage and current. These days, you never know. There's such demand on what we call firmware that people may have absolutely no idea about their physical layers and their electrical, draw. So the next thing you do is you blow it out. Total reset. It may be that it can't be blown out. Bootloader locked. Dome, dome, dome. So if it's not bootloader locked, then you load either your test code or production code. If it is bootloader locked, you either reject it or you accept it. All depends on your policy. Once that's done, output off, delay. Output on, delay. Measure. You delay for settling times. It takes things time to settle. Different supplies can settle in different periods of time. There's the settling of the actual signal and the settling of the measurement. Do whatever you need to do. Usually, it's establish communication. Ping check is what I usually call it. That's when you get to the good stuff. It can be at any layer of the stack. Sometimes you just call a third-party function. Tells you yes or no. Sometimes you'll dial in very, very, very commonly. You'll dial in a terminal prompt over whatever medium is there. You can have a terminal prompt at a UART, at an SPI, at a Ethernet port, CAN, RS-485. Bluetooth, Wi-Fi. It all depends on whether the person made an operating system. It's usually nice to make a small OS, responds to commands, communicate with it. You might be writing additional settings. You might be reading off. This is the point where you can read off unique numbers. Many chips have a unique identifier. People like to try and track by the unique identifier inside of a chip. And they fucking swear by that. And that's because they're coming from mega high volume cell phone industry where everything is too small for stickers or laser markings and too compact for a reason. And so they basically have to gamble that they'll be able to read that value. Now, if anything goes wrong, you can't get to that value. It could be you could read it off the chip or some subset off the chip, but you can pretty much assume that value is lost unless it's laser etched on the top, and it won't be scannable. You can read it with machine learning in the right light. You know, you put a camera over it at the right angle with the right light, if that's the same number. It's probably not. So I'm not a big fan of tracking by internal serial number. What it is they don't know how to generate a fucking unique number. And so they're like, these guys have one. It's like, yeah, there's lots of unique numbers. Everybody's got one, you know. I'm not impressed at all by other people's unique numbers. You know? Creating a serial number is not a complicated task. You need a single source of truth. You need a mechanism by which to check. You need a generator. Usually, check something like the date. You don't necessarily want like a 9-digit number. It's kind of excessive. It's a lot of characters for not much counting. So you limit the number of characters or numbers and throw some alphas in there. Alphanumerics hold a lot more data than numbers. You can put more information in a smaller space. This improves reliability. By reducing barcode density. Look at the FedEx barcodes, UPS. They get the shit kicked out of them. So you write down anything that's in there. Many steps to the text. You'll be able to tell right away whether you can turn things on or off. It's always good to have the ability to turn peripherals on or off. If there's no ability to turn peripherals on or off, then there's an assumed loading, which is characterized. That's the power of all peripherals for a given firmware on a given hardware set. You measure it, and then you set a limit. Depends on how much deviation you want to accept. It's your first spot to find a problem. If you're running insufficient current, something's not taking a load. There might be 1, 2, 3, 4, 5, 6, 8 loads. You know there's going to be a problem. That, or the firmware changed, or next assembly changed. So it's something that pretty version dependent, revision dependent, the kind of thing that gets adjusted. Usually I'll just open up the window on stuff like that because I don't appreciate what it's doing. If you have the ability to turn peripherals on and off, you go and turn each one of them on. First, you always check power. So turn each one of them on and off. Assuming you're starting in an off state, you turn the first one on. You expect an increase in current by a fixed amount, pass or fail, inside of these bounds. 5 milliamps, 37 milliamps, whatever it may be. You take a rough measure on this. If you turn it on and it doesn't draw additional current, it's not electrically connected, or the switching circuits are broken, or the fixture is broken, something like that. So you can play them like a pipe organ, one at a time, or you can turn them on in sequence. Matters not. It's probably an easier test to turn them on one at a time, if that you can do that, to not have to do cascading corrections. Cascading corrections are obnoxious, right? It's like this plus this plus this, and it should be within this range. It's more error as well. So if you don't have the ability to turn things on and off, you're just looking for a sum current, you stop right there. Say, nah, the baseline current draw is too low or too high. Too low, something's fucking not turning on. MOSFET open, things like that. Pins open. Too high, circuit in failure mode. Something's fucking hitting its rail, going thermal, something like that. So we make a pass on the power and bail on that if anything's running funny. Like, there's no sense in doing comms checks until you've asserted that your power is right. Many things, people will skip that step. They don't look at what it's drawing, and they keep trying to talk to it. They can talk to it for like a few seconds, and then they can't talk to it. It's like, dude, what are you doing? You know, what are you fucking doing? Because the circuit's like in an overheat cycle. Like, some part of it's shorted, and it's dumping a bunch of current, and it's heating up, and it's thermally shutting down. So, you know, they're fooled because they can boot it up and talk to it for like a second or a minute. This especially happens when you miss heatsink compound, shit like that. Be sensitive to heat sinking. In tests, you don't run things for very long. You just turn it on for a second. Make sure it works. But if something's drawing irregular power, you don't talk to it. Off to the side. Save you a lot of time. So if all the power checks out, you communicate with it. If you're running your own firmware, you can go infinitely freaking, you know, permutated, but it's not called for usually. If you're running a factory firmware, just do a factory query. You get an expected response. It can be anything. Mumbo jumbo. If you have stimuli, like a small electromagnet, measure, turn it on, measure, turn it off. no stimulus measurement and a stimulus measurement. Just looking for a binary. Is it present? Presence detection. Got shit spilling down the screen over here. I don't know what that is. Do this for all your peripherals. The low-hanging fruit is to start with known registers. Serial number, known program states, like should be 1, should be a 10, should be a 100. Simple checks. Depends on how tight you want to lace them up. Sometimes you want to lace them up tight. There's no wiggle room. And we'll fucking break everything if they change anything. I mean, you can lace them up real tight if you want to. Like mapping timing. You watch it, take an arbitrary measurement, you look for a noticeable change, you write down that timing, you show that it's consistent, you add that to your checks. It's profiling the current draw of the firmware. If they change it, breaks. You can do it. Like Crocodile Dundee, you can eat it, but it tastes like shit. You're always having to fucking go back and forth. So figure out how tight you're gonna lace them. Take a good measurement of any temperature sensors. Most chips have an internal register these days that you can measure. Degree of C. You can have a wide range there. You're looking for relative measures. If you measure the chip core and it's 30C, you might expect this one over here to be, depends. How fast is the tester cycling? Is there a fan blowing in there? So you don't want to neck down too tight. You're looking for a sane number between cold room temperature and a hot operating. It is not a calibration stage. Presence. Just writing down a baseline. It's actually quite important to track temperature with any measurement because that allows you to perform an offset. Some things draw a lot more power when they're hot or they're cold. They have a bunch more skew. Temperature compensation is a very normal thing. If there's any fans, turn them on and off. If there's any lights, turn them on and off. You measure the current for all of these. I'll tell you if you're all fucked up. If there's any external load switches, turn them on and off. If you're dumping into thermal loads, those are going to be safe, like resistors. I really prefer to dump into a fan, dude. It's like the best fucking load you could ever want. You get them in 12 volt, 24 volt, 36 volt, 48 volt. Covers most things. Now maybe the intended purpose is to drive 24 volts at 5 amps. It's like, okay, put a 24 volt fan on there that draws 3 amps. Perfect. And the thing is, you go and try to put a 24 volt 5 amp resistor in there, it's like 120 watts, dude. And if anything goes funky in the tester, it'll smoke show. So anytime you have passive loads, resistive loads, you have to have a thermal cutout switch on those. You buy them on Amazon, little thermal switches, 60C, 120C, they cut out at a certain temperature. And you use a thermal epoxy or a capped-on tape to mount them to the load. And you run the current through the switch into the load, and it will open if it gets too hot. This will stop smoke from coming out of your fixture. The trouble is, it also put the fixture into a real fucking strange state. Or if you walk away and get lunch, you come back, it works. If you run 3 in a row, it stops working. So a fan is a nice load because it doesn't overheat. In fact, it cools down. It's a good DC load. Drive each load in sequence, make sure that it draws what you expect. That's why testers make weird sounds. Clicks, clacks, buzzes, hums. It's just going through the various channels. And you might think that circuit doesn't have anything that hums or buzzes. It's like, yeah, just a load. It doesn't matter. And some people who are, dude, let's talk about that group for a minute. The group of superstitious circuit people who haven't the fucking foggiest how electricity works, and so they survive through superstition. They're like, oh no, that's not the intended load. You couldn't run that. No, I believe that could damage the circuit. I have to run those people right the fuck out of the room, dude, right away. Because they don't know what the fuck they're talking about. Like, they got some kind of switch, turns on and off. They've had trouble in the past. So they fucking finesse it into working. Some kind of MOSFET switch, turn it on like, 50 volts at 10 amps. It's a hard thing to switch. All kinds of inductive flyback, all kinds of capacitive inrush, right? All kinds of fucking programmable fucking shunts and shit, dude. It's the oldest story in the book, dude. So people develop a superstition. And they might go so far as to characterize their fucking impedance, dude. They're like, you can only hook up this exact impedance of resistance, capacitance, and inductance. Immediate fail. Immediate and total fail. You're rejected from the fucking production line. Unacceptable circuit. A DC switching circuit will fucking switch anything, dude. Solid state doesn't care what the capacitive inrush is, as long as it's not fucking obscene. It doesn't care what the inductive load is, as long as it's strapped with flyback, and it better be. Fucking always strapped with flyback. TVS flyback. Right? So long as there's sufficient current driving margin to make it through the fucking inrush stage. I've seen people release products with like fucking TO220 MOSFETs rated for 200 milliamps on like a safety circuit. You're like, what the fuck, dude? So easy to blow that. What are you talking about? It's because they don't understand the electricity. And then superstition evolves. So people will tell you, no, that circuit's not supposed to run a fan. And I say, yeah, it is. That fan is just a BLDC controller with a little bit of input capacitance, and it fucking draws current. It can and will suffice. It is perfect. Can I drive that? It's one of my filters. Go back to school. In fairly recent times, I've run into some superstition around various things. It's not to be tolerated. Electricity is easily understood. You'll have AC, DC, pulse power. It's going to be either high voltage or not. It's going to be high current or not. It's going to be high speed or not. Most DC circuits these days are either just on or off, meaning they're a power switch, or they're switching. If they're switching, they're actually AC. It's called pulse power. It's pulsing. Keep zooming in on the scope. You'll see the pulsing. They got 100 names for it. I keep getting fucking shit spelled on the screen. They got 100 names for it. It's a PID loop running PWM somewhere at the end of the day. The analog days are long past. You simulate analog by really fast digital. 20 kilohertz, 50 kilohertz, 500 kilohertz. So you can run whatever load you need to. It's an AC load. Don't matter, dude. Just throw something on there. If it's big AC load, dump into mains, regen it. Hang something off of it. Fucking dollar store heater. A laptop charger. It's very, very easy to draw 500 milliwatts, 5 watts, 50 watts, 500 watts, 5,000 watts. You apply a representative load. Sure it doesn't overheat. That's why fans are useful. Use LEDs too. You can use large thermal masses. At home I do shit like that. I take dead pumps and stuff like that. Like at a certain point, if the mass is large enough, something like 200 watts, it can continuously shrug that, barely getting warm. It'd take like a week to thermally soak, because it's made to shrug heat, right? Even the slightest convection cooling or fan cooling will stay cool. So anyways, you do your functional tests. Pass or fail on every one. The first fail, you bail. File a test report. Local to the cloud resources. Careful of filing to your cloud resources. It's always important to deploy. Many a script depend on a resource which is domain dependent. So something like AWS is not domain dependent. You can make it domain dependent, but it's not. Something like a third-party data store, MongoDB, or any of the fucking services that it require you to be on a given domain to store to their repo. Then there are domain-based services which are working in a different security stance. They'll give you easy access. That's because you're already tokened in, right? You're already logged in. This is where you're logging in with an account. And that's fine. You can do that. You want a drone account for that. You set up a testing login that has limited scope. So it's on the domain, but it doesn't have privilege to go anywhere but one spot. Make sure it stays logged in. And that's why it gets fucking annoying if IT has like a timed blowout on things, or so it's to be avoided. You don't use username and password unless you fucking have to. You strongly prefer tokens. Public-private, dude. You gotta have a token rolling mechanism. It's best to do that while your token's still valid. Like, it's always a security, you know. Like, the whole fucking security industry could use a major overhaul. But if you've already got a good token, you can pass yourself a new token. And then when your fucking token stops working, you can use the next token. How many tokens do you have that you check? Do you just try one? Why would you not have one and then another? Otherwise, you gotta go put hands on. You think every time Tesla needs a new token that all the cars stop on the road and someone runs out there with a USB-C thumb drive and sticks it in and loads a new token? No, it's not how it works.